Welcome back. In this video, we're going to work on some extra practice problems dealing with learning objectives throughout all of chapter 13. Pause the video and try this problem on your own, and then I'll walk you through a solution afterwards. Welcome back. So the question asks, how much energy is needed to vaporize 10 grams of water? So the vaporization process is where we take a substance in the liquid phase and we convert it into the gaseous phase by adding energy. In order to calculate the amount of energy required, we can relate this to the enthalpy of vaporization and the amount of substance we have. Because you're given an enthalpy of vaporization in kilojoules per mole, we need to know how many moles of water we have. To find the moles of water, we can take the mass of water and divide by the molar mass. That gets us just over 1/2 of a mole. When we multiply this value by the enthalpy of vaporization, this computes the energy required to do the process. In other words, the energy required to vaporize 10 grams of water is about 22.6 kilojoules. Here's another question. Pause the video and try this one on your own, and then I'll walk you through it. Welcome back. So for this question, we have 30 grams of water that's cooled using liquid nitrogen. Enough heat was removed from the water to vaporize 110 grams of liquid nitrogen. If the water is initially at 87 degrees Celsius, what's the final temperature? My recommendation when you're solving questions that involve transfer of heat is that you use a heating curve to represent the process that's occurring. So let's do that here. For nitrogen, it says that we're vaporizing it. So if we're vaporizing it, then we're going from the liquid phase to the gas phase. And we have 110 grams. For water, we know that we're starting at 87 degrees Celsius, and you should know that water boils at 100. It freezes at 0. So we're starting here, 87, and we're decreasing the temperature. Now the problem is that we don't know what our final temperature is. So we can't fully draw a phase diagram or a heating curve for it yet. So where do we go from here? Well, we know that the liquid nitrogen, all that's happening for it is the vaporization process. So if we calculate the amount of energy that is absorbed by the liquid nitrogen, that's going to be equal to the amount of energy that's released by the water. And then we can calculate the final temperature. So note that our standard or constant values are all in energy per mole. And so let's start by converting the mass of each substance into moles. So we can do that by dividing the mass by the molar mass. We do that both for water and for nitrogen. Now, let's calculate the amount of energy required to vaporize the liquid nitrogen. That's going to be the number of moles times the enthalpy of vaporization. So it takes just under 22 kilojoules in order to vaporize the liquid nitrogen. That means then that the energy that's given off by the water is negative 22.81, excuse me, let's leave some more room for that. (22.845 kilojoules. Now we can calculate the final temperature. And we can do that because we know that we know the specific heat and we know the energy that's involved. So we can calculate the amount of energy required Let's say in this case, we were to go to 0 degrees Celsius. By finding the energy required to do that, we can compare that and see if we have overshot or if we still have energy left over. So the energy required to cool down the water to 0 degrees Celsius is found by taking the molar heat capacity times the number of moles and that change in temperature. What we see here is that this is much less than the total amount of energy that's given off. So at this point, now we need to find out what other processes we do. So after we cool it down to 0, the next step would be to start to freeze the water. When we take a look here, we see that it's 6 kilojoules per mole, and we have just over 1.5 moles. So that's going to be about another 9 or so kilojoules that's given off, and we've already given off about 11. So we probably will have a little bit left over. Let's confirm that by calculating the total amount of energy that it would take to freeze the water. That's done, again, by calculating, multiplying the moles of water times the negative value for the heat of fusion. And that's because what we're doing is the freezing process, which is the opposite process of fusion. That would give off just over 10 kilojoules of heat. If we add together the amount of heat that is given off, what we will see is that we have a little bit left over, and that heat is equal to just under 1 kilojoule. And so what we see then is that there's a little bit more heat that's given off as the solid ice cools down. And now what we can do is, since there's no process that's going to happen after cooling down, since we already have the solid, we can determine the final temperature of the ice now. Let's convert into joules, and then we can use the relationship between heat, amount, and temperature. We know the molar heat capacity, the number of moles, and we can solve for the change in temperature. We see that our change in temperature is 14.4 degrees Celsius, and it's decreasing by that amount, which means then that our final temperature is going to be the difference between our initial temperature of 0 and then the change in temperature, which is negative 14.4. And so our final temperature is negative 14.4 degrees. All right, here's another problem. Pause the video and try this one on your own, and then I'll talk you through a solution. Welcome back. So we want to know, what's the boiling point of the substance shown if the pressure is at 15 atmospheres? All right, the easiest way to do this is to try and draw a line that's going to depict the pressure. When we're talking about the boiling point, we're talking about the temperature at which we convert from a liquid to a gas. The curve on the right here represents the coexistence of liquid and gas, and therefore represents the vaporization process. So if we are looking at a pressure of 15 atmospheres, that's going to correspond to about 50 degrees centigrade. If we wanted to find where do the other values show up, well, at 0 degrees Celsius, we have a pressure of about 10 atmospheres. 200 degrees Celsius corresponds very closely to the critical point. And negative 15 degrees Celsius we can see is corresponding to our triple point. The last option, E, the sublimation process is going to occur anywhere along this coexistence line. So at pressures of a bit below 10 and temperatures below negative 15. All right, here's the last problem for this video. Rank the following substances in order of increasing vapor pressure at any given temperature. Pause the video and try this one on your own. Welcome back. So we know that the stronger the intermolecular forces will lead to high boiling points and low vapor pressures. The reason for this is because if a substance has high intermolecular forces, it's attracted to itself. When we're talking about vapor pressure, that's the pressure of the gas when a substance is evaporating and goes from liquid to gas. So if there's high intermolecular forces, there will be a low tendency for a substance to break the intermolecular interactions and to convert to a gas. So let's evaluate the intermolecular forces. None of these molecules can perform hydrogen bonding with identical molecules. Molecule number 3 can interact through hydrogen bonding, but only if there is a donor nearby, since it's only an acceptor. Molecule number 3, however, is polar, and therefore it is most likely to have the highest intermolecular forces. But let's take a look at the other factors. They all have approximately the same molar mass. A difference of 2 grams per mole is not significant when their overall mass is over 100. So for all intents and purposes, their molar masses are identical. However, there are differences in terms of their shapes. Molecule number 2 is much more compact than both molecules 1 and molecule 3. Therefore, we can differentiate between all 3 molecules. The most important factor overall is the polarity of molecule number 3. After that, we then take a look at the shape of molecules number 1 and number 2. Molecule number 1, being more elongated, has more intermolecular forces because it has a larger surface area. Therefore, if we wanted to rank these in terms of increasing intermolecular forces, that would be 2 is the lowest, and then 1, and then 3. However, we're wanting to rank these in terms of increasing vapor pressure. And we know that high intermolecular forces means low vapor pressure. So to rank them in terms of their vapor pressure, we would have the reverse. Okay, that's it for this video. Thanks for watching. Have a great day.